Since it's time, I think we can get started. Today is Charles' third lecture. Please, the stage is yours.
Thank you, Benoit. Okay, so what have we seen so far? I will. So we have seen that we have defined an object which was this spectral. We were taking a graph which was locally finite. Okay, and what if we were taking a vertex of the graph, we were defining a spectral measure at a vector. So here it's the direct mass at X, whose moments, if the degrees are bounded, if degrees are bounded, uniformly bounded, the moments of this spectral measure was equal to the moments of the powers of the taking powers of the adjacency operator of this matrix. Okay, so if the graph was finite, this spectral measure was depending on the this spectral measure depends on the when the graph is depends on the orthogonal basis of eigenvector or the full spectral resolution of the operator in the general case. So, and we were trying to define something which was the empirical distribution of eigenvalues. So, which we have found a general framework to define that. It is in the framework where G is a uniform. So, where G now has a distinguished vertex, which is called the root. It's a random graph, okay? It's a random rotated graph, which is unimodular, random rotated graph, with low. If we consider a unimodular graph with low, where's my pointer? Here, with low rho, okay, so what does it mean? It means that so rho is a probability measure on rotated graphs, which I was denoting like that. And the fact to be unimodular implies that it satisfies a mass transport principle that you can write. It satisfies for all functions where this makes sense, meaning where you, for example, the non-negative functions, such that the expectation of the sum over, so the function f should be, I put the, so the function is, for example, on the set, lives on the, takes a non-labeled doubly rotated random graphs, a non-labeled graph with two roots, okay? By unlabeled, I mean, so you can, this function which is invariant by taking any isomorphisms which preserve the two roots and leaves the, okay? And so this function leads to any function on any doubly rotated graph, okay? And so it will be unimodular if it satisfies this mass transport principle for all such functions, okay? Okay, so when you are unimodular, we define the spectral measure at the spectral measure of the graph as being mu rho, which was the expectation of under its distribution of the spectral measure at the root. Okay, and this definition had some. So this is a definition of unimodularity. Okay, so this definition has two advantages: that if G is finite, if the graph is finite and U of G is the law of you take a uniform root O and you look at the connected components, then what you get is that the mu of U of G is simply denoted by mu G is the empirical distribution of the eigenvalues. Sorry. Maybe. Okay, so you retrieve the empirical distribution of eigenvalues. Okay, so taking the when in the setting of unimodular rooted graphs, you have defined a spectral measure, which is nice because it will not be, we'll see that later on. It does not, it is kind of invariant under unitary transform as the empirical distribution of eigenvalues is. Okay, I think that's where we were. So maybe I will give you, I didn't insist a lot about this unimodularity. I will give you one lemma, which is called everything shows at the root, which is you can find in this Aldous-Lyons paper on unimodularity, as I call it that way. You can state it like that. Take a function f, a measurable function f on rooted graphs, okay, to, let's say, R plus, such that rho almost surely f of GO is 0, okay? For example, okay, f are kind of f of GV is an indicator, for example, that GO belongs to some Borel set for topology, okay? Some set, okay, for example. This is an example. So, and rho is unimodular here. Unimodular. Okay, so imagine that you have a unimodular random rooted graphs. You have found a function such that rho almost surely the function is 0 on the root. Then rho almost surely for all vertex of the graph, f of GV is 0. Okay, so this is called by Aldous and Lyons everything shows at the root, meaning that in fact all information of the graph is encoded in the root. Okay, so let's prove that. I mean, it's a 2 line, so it's nice to illustrate how you can illustrates how you use mass transport principle. So this is called unimodularity or mass transport principle. Okay, so what do? You define the function f on G tilde to R plus, defined by f of G U V is equal to f of G U. Okay, it's not. It's an example of such function, and you apply the mass transport principle. What do you have on the left-hand side? You have the expectation of rho of the sum of over all vertices of f of G O should be equal to the expectation under rho, so here I forgot the rho, of the sum over all vertices of f of GV. Okay? But the assumption implies that this is 0, okay, because this is almost surely 0, and you sum the countable number of times 0, so it's 0. And so this is 0. So since all these guys are non-negative, it implies that for almost surely, for all V in V, f of GV is 0. Okay? So the proof is 1 line, but it illustrates this unimodularity and how you use it in practice. If you are curious about why is it called unimodular, it is called unimodular in reference to the fact that the R measure on countable groups is unimodular, meaning that its R measure is left. The left R measure and the right R measure are the same, And if you consider the counting measure on the group, you will see that it satisfies this mass transport principle. And in some sense, this will be the invariance on the multiplication on the left, and on the right-hand side, it will be the multiplication on the right. So that you can look in my notes, you will find more explanation. Okay, so now that we have put this setup of unimodular graphs, we will study the continuity, because we are mostly interested by spectrum, continuity of spectral measure. Okay, so we will, I want to prove this theorem. I will not exactly prove it, but so let's take rho be unimodular. U be unimodular. Okay, rho is a law of some random rotated graphs. Okay. Then you have some. So rho belongs to, I think I was denoting that by rho uni g dot. Okay. Okay, sometimes you can put a tilde or not, meaning you recall. Okay, so when I don't put tilde, it means that the graph can be rooted, can be labeled. Okay, and then I should write explicitly the vertex set, but okay, I abuse the notation and skip this detail. Okay, so if rho is unimodular, then the rho almost surely the adjacency operator of G is essentially self-adjoint. Okay, which means that the closure of A is equal to its dual, almost sure. Okay, so in particular, we have seen that in particular, mu rho is well defined. Because we have seen that, I recall you, that to define the spectral measure, you have to define the spectral measure at a vector. You have to require that the vector that here the direct mass at X is in the domain of the operator, and that the operator is self-adjoint. Okay, so if this is not the case, then this spectral measure is ill-defined. Okay, so this first point says that whatever, as soon as you have unimodularity, your adjacency operator is automatically self-adjoint, and so that's nice. And the second one is it's a continuity property. Okay, but if rho n, if you have a sequence of measures, okay, so which are all unimodulars, okay, rho n, if they converge to rho for the local weak topology, then the spectral measure of rho n converges weakly to mu of rho. Okay, we will see later on, I mean today, we will see a refinement, a refinement of that. Okay, so I should say, so the weak topology is a convergence of all bounded continuous function, right? So let's start with so I will not exactly prove that. I will prove a weaker version, which will what will be needed in this course, but I will give you some to sketch why I is true in general. Okay, let's start with the lemma. Look at the function which at rooted graph associates the spectral measure at the root. Okay, and you consider this function on the set of graphs, on the set of rooted graphs, such that the degree of any vertex in G is bounded for. Okay, let's suppose that G delta. Okay. So look at this function. So you look at the set of unable graphs which have a uniformly bounded degree. So the claim is that this function, so the function is continuous for the local topology. Okay, so here, to be precise, here I put the set of, on this set, I put the local topology, and on this set, I put the weak topology. Okay? Let's check that. This is easy. So you just have to remind the definition of the weak topology, the local topology, and the characterization of the moments of the spectral measure. Okay, if you take d mu g dx, okay, d0, let's say, this is, sorry, here I should put a 0, it's a typo. So the case moment of this measure is equal to the number of closed walks from O to O of length k. Okay. In particular, if you have two graphs, let's say G1 O1 and G2 O2, two rooted graphs, which are isomorphic, let's say up to depth, up to radius. So this is a good time to recall you this notation. When I have a rooted graph, this denotes, when I put a subscript here, an integer subscript here, it means that I'm just looking at the subgraph, the rooted subgraph, spanned by the vertices which are distance at most h, graph distance at most h in the graph. Okay. So if you have two graphs which have the same h neighborhood, I mean, such that their h neighborhood are rooted isomorphic equivalent, okay, then these moments, the number of walks, they will be exactly equal. The number of walks so maybe I should put a number here. The number of walks will be exactly equal as soon as k is less than 2h. Okay, because if you have O1, you look at a path of length k in the graph, it has to remain, the walk has to remain inside the ball of radius. Has to be cannot go further than the ball of radius centered at O of radius k over 2. Okay. And so if these two, since it counts number of walks, this is the number of, if two graphs are isomorphic, the number of walks are just the same. So if two graphs are rooted isomorphic, you get this remark that the moments are the same. Okay, so now you can prove that. The lemma then is simple. If Gn O converge to GO, okay, maybe I can put for the local topology, it means that there exists Hn, it's equivalent to say that there is Hn which goes to infinity, such that Gn On of depth Hn is rooted isomorphic to Go of depth Hn. Okay. In particular, the moments of will converge to the moments. I mean, they are equal after some steps. The moments will converge to the moments of the limit for nk. Okay, and since the support of mu gn Dirac mass at ON is included in minus delta delta. Okay, because the assumption is that the degrees are bounded. Then all these measures are characterized by all these measures are characterized by their moments. Okay, so if the moments converge, I have to converge weakly. Okay. So this is for the lemma. So it implies 2i if you restrict, of course, this implies 2i if you restrict to bounded degree graphs. Okay. So what I will do, I will prove a small, an easier version of the theorem. Okay, I will prove the following proposition. So rho unimodular. Okay. Let's say that it is Sophic. So I recall you that a measure is Sophic when it's spectral. When there exists a graph which converges in the Benjamini-Schramm sense to rho. Okay, so maybe it's not necessary to write it here. So you take a rho unimodular. Okay, the claim is that there exists a probability measure, mu rho, okay, on R, such that for any sequence of graphs, GN sequence of finite graphs, such that, okay, so GN converges in the Benjamini-Schramm sense to rho. So this is another word saying that when you route uniformly at random, this converge for the local weak topology to rho. Then mu of Gn converges to mu of rho weakly for the weak topology. Okay, so this is a proposition which is weaker than the main theorem. Okay, because it proves essentially, it doesn't say that the spectral measure is the adjacency operator of the unimodular graph is self-adjoint. It only says that you can define a probability measure with good continuity, which has the good continuity property. Okay, so this is easier to prove. I will prove that, and then I will sketch you how you go to the full theorem. You start with a lemma, which is a consequence of the courant Fisher min-max formula. Okay, which proves, so it's a consequence of this courant Fisher min-max formula, which says that if you have two matrices in ML of C, okay, which are Hermitian, if you have two Hermitian matrices in ML of C, then if you define mu A, which is an empirical distribution of the eigenvalues of A. Okay, so this is the eigenvalues are real, and you do the same for mu B, and you defined the Kolmogorov-Smirnov distance of two probability measure, which is classically defined as a supremum of the L infinity norm of their partition function. Okay, so this is a Kolmogorov-Smirnov distance. Kolmogorov-Smirnov distance. Okay. And so you have defined mu. So it's a bound. So it's a concept. So the lemma is not the courant Fisher min-max identities. It's a consequence of them. A consequence is that the spectral measure, the distance in the Kolmogorov-Smirnov sense between the empirical measure of mu A and mu B, is always bounded by the rank of the difference of A minus B divided by N. Okay, so so the proof is an exercise. Okay, I recall you maybe the Courant-Fisher variational formula. So the Courant-Fisher min-max formula, what is that? If you order the eigenvalues of your Hermitian matrix A, it will say that lambda k of A, the case largest, is equal to the maximum, the supremum over all subspace, over all vector subspace in C power n of dimension k, of the minimum over all x in H, which are of unit Euclidean norm of x, so maybe usually given by phi the vector, so I will continue to do that, phi A phi. Okay, so this is the Courant-Fisher formula. So the exercise is to deduce from this variational formula for the eigenvalues of Hermitian matrices this lemma. Okay, so with this simple lemma, with this classical lemma, we can prove the proposition by a truncation argument. How you do that? A proof of the proposition. Okay, so let's assume for simplicity that so we'll consider a sequence of graphs, mu of Gn, and we will prove that they converge to something, okay? So let's assume for simplicity that the cardinal of Gn is n, and An will be the adjacency operator of Gn, and you defined a vertex set Vn maybe delta as being the set of vertex of the graph, such that if you look at the ball in Gn, so if you look at the set of vertex at distance, which are neighbor of, which are V or the neighbor of V, so for all U in, so for all vertex which are U or which are neighbor of which are V or neighbor of V, the degree of, which are of degree less than n. Okay, so it's a subset of the vertices where you consider only vertices such that they have of degree less than n, and all their neighbors have degree less than n. Okay, and you set a n. Okay, let's maybe put delta. You define a n of delta of xy to be a n of so it's an adjacency restricted to the n, where you times indicator that x, y belong to V. Okay, so this is the adjacency operator of an restricted to Vn delta and extended to the whole space by putting just zeros. Okay, so the rank of an minus an delta, okay, this is bounded by the number of non-zero rows of this matrix, okay? So this is bounded by n times the probability, sorry, maybe I should write it, number of non-zero rows of an minus an delta, okay? So this is, if I can, you can write this number in terms of this. I can write that in this way, that let's call maybe, okay, we need a notation. So this event, okay, let's call it E of Gn of V, okay? So the fact that for all vertices, okay, so that's the probability that E Gn of O is a complementary of that. Okay? And let's call this number epsilon n of delta. Maybe it would be, okay, sorry, I will change my notation. I will write it very explicitly as a rooted graph event. Okay, in this way, that's fine. Okay. Okay, so you agree with my notation. So when I write according to a prob measure, the rooted graph, I denote it by the canonical rooted graph, I denote by GO. Okay, so this is the number of non-zero rows. It's bounded by this the complementary, the probability of the complementary of this event divided by times n. Okay. Now, so this is n times epsilon n of delta. Okay, so this is a local event because it only depends on the neighborhood of radius 1 of the around the root. Okay, so since Gn O okay, since U of Gn converges weakly to rho, epsilon n of delta converges to sorry, I put a delta and here I put an n. So it was delta, sorry about that. It's a lot of typos. En of delta converges to epsilon n to epsilon of delta. Okay, which is a probability that under rho that the EGO complementary out. Okay, and epsilon, since the graph is locally finite, rho, which is a law of a locally finite graph, meaning that all vertices have bounded degrees, epsilon of delta goes to 0 as delta goes to infinity. Okay? Hence, epsilon n of delta is smaller than epsilon for all n if delta is sufficiently large. If you fix any epsilon and delta will be less than epsilon if you take for all n large, if delta is chosen sufficiently large. Okay, so now you can come back to the you want to prove we will prove that this spectral measure forms a Cauchy sequence. So you take m and n, two integers. Okay. You look at the Kolmogorov-Smirnov distance between the adjacency matrix of AM and the adjacency matrix of AN. Okay, sorry. So this I used to denote then by GM and GN. Okay, so you apply. So this is less. The Kolmogorov-Smirnov is a distance, so it's less than the adjacency matrix of okay, so A was okay. It's just that I have too much notation for this denoting the same object. You have this is less than that, plus the Kolmogorov-Smirnov distance between AM of delta and AN of delta. plus the Kolmogorov-Smirnov distance between A n of delta and mu of A n, right? So this will be less than 2 times epsilon plus the Kolmogorov-Smirnov distance between A and delta and n delta, sorry, and A n delta. Okay, so this is simply the spectral measure of a rooted I can also write that as a spectral measure of a finite rooted graph. Okay, so by the lemma, which was this lemma, this lemma, that the spectral measure is continuous for the local weak topology when you restrict to bounded degree graphs. Okay, so Gn U of Gn converges in the Benjamini, so converges to rho. This implies that U of Gn delta, which is a graph obtained by restricting, only keeping the vertices. So Gn is a graph where you Gn is a graph with the same vertex set at Vn and edge set En delta, where E belongs to En belongs to En. So it's a subgraph. So E, which is a pair xy, if and only if x, both x and y belongs to this set Vn delta. Okay, so where you only keep vertex. Okay, so by the lemma, so E and G, this U, G, and delta will converge to some measure, to the measure rho delta. Okay, which will be the law of G delta O. Well, G delta is exactly formed by you just remove all edges. You just remove all edges which are adjacent to a vertex which has degree at least D delta. So, okay, so this will be less than 2 epsilon plus epsilon prime. Okay, because due to that, we know that mu Gn delta, the spectral measure of Gn delta, which I also write like that, will converge to the spectral measure of rho delta by the lemma, by the continuity lemma. Okay, so these two guys, they converge to the same object, so they are in Cauchy, they form a Cauchy sequence. And so you have proved that the Kolmogorov-Smirnov of so this guy I also denoted like that, and this guy, this is the same object. So you have proved that the spectral measure of the spectral measures form a Cauchy sequence. Okay. Thus, mu of Gn is a Cauchy sequence. Okay, and the set of probability measures on R equipped with the local topology is complete. Okay, so they must converge. So they converge to a measure mu rho, which is a probability measure on R. Okay, so then you have to check that this mu rho does not depend on the sequence, but it's not very hard. Okay, so this is the idea of how you prove this proposition, that if as soon as you have a unimodular measure, you can define a probability measure mu rho where such that the spectral measure, so if you have, when you have a sequence of finite graphs which converge in the Benjamini-Schramm sense to this measure, then the spectral measure will converge also to this measure mu rho. Okay, so but for the full proposition, the full theorem was more demanding than that. It was saying that as soon as you had a unimodular measure, the adjacency operator was essentially self-adjoint with probability 1, and also this continuity property. Okay, so I will just hint, you can look at the note how I do that, but the key is to define, when we mention the group algebra, the fundamental algebra associated to a group, so it's a group fundamental algebra. And we saw, I said that the adjacency operator was one element of this group algebra. So here also there is a group, there is associated to any unimodular measure. There is a fundamental algebra, which I will define now. Okay, so to prove the theorem, it is necessary, I don't know, but we use the fundamental algebra associated to any unimodular measure, any unimodular probability measure. And this fundamental algebra is equipped with a tracial faithful normal state, which I will now define. Okay, so I will sketch it because I don't want to make a course on fundamental algebra. So I will just sketch for those who know how do you build this fundamental algebra. And for those who don't know exactly what is a fundamental algebra, that will be fine. I will not insist more on that. Okay, so you consider the set L infinity of first comment. So we fix be the set. We look at a labeled, something labeled because it's easier. Let G with a dot be the set of labeled graphs with vertex set V, which is the integers. Okay, rooted at 0. Okay, so I consider the set of graphs which have a countable, infinite number of vertices, which are rooted at 0, and I denote this set by G bullet. Okay. So now I will consider, if I look at the as a set of the fundamental algebra will be a subset of the set of random operators on this random operators on L2 of V. Okay. Okay, so an element T, okay, is a random operator, is a random bounded operator, almost surely bounded operator. So it's a rho almost surely, so I should put rho here. Rho almost surely bounded operator on L2 of V. Okay, so I look at the set of rho almost surely bounded operators on L2 of V. Okay, so now I will, the fundamental algebra is a subset of those. And when you define the group algebra, you consider the set of bounded operators on L2 of gamma, where gamma is a group, but you consider only those who are which commute with multiplication on the right by group elements, and this gives you the left fundamental algebra. Here you do the same thing. You impose some extra commutation, and so M is a subset of this L infinity of a subset of operators which commutes with the bijections of on M, which commutes with the bijections on V. which is n here. Okay, that is that T. If I write an element here, I can write it as the set TGO. Okay, I want it to be equal to, if lambda of sigma is the operator lambda of sigma, if sigma is a sum bijection from V to V, so an integer, lambda of sigma of a Dirac mass at X is the finite delta of sigma of X. Okay, I want that TGO is equal to lambda of sigma minus 1, T of sigma G of O of lambda of sigma. Okay, so in particular, if you think about that, the graph I'm considering, they do not, in word, they do not depend on the choice of the root. Okay, in particular, TGO is equal to T of sigma GO rho most shown. Okay, this should be equal to rho most shown. Okay, so what I mean by that is that they do so TG is what I mean by that. So these graphs, in fact, they do not depend on the choice of the root. Okay, okay, so they are invariant under rerouting. Okay, this is exactly the kind of operators that, for example, the adjacency operator, when you define it, it does not depend on the choice of the root. Okay, so you don't want to define an operator which uses as in its definition the choice of the root, the position of the root. Okay, so then when you do that, so this is this form of fundamental algebra, and you have a trace. You define the trace on top of if T is in M. You define the trace, which is the expectation of direct mass at T delta. Okay, so this is a. It happens that this is a faithful normal trace on N. I think there is only one L in faithful. I'm not sure. How do you prove that? Do I have time to do that? Okay, one word. We just so you define and then when you have a fundamental algebra equipped with a faithful normal trace, for example, there is an analog of the Courant-Fisher identities, which is true, and then you have also some general result by Nelson, which says that all operators, which are essentially all operators which are affiliated to fundamental algebra, are self-adjoint, and so you use some general tools from operator algebra on fundamental algebras to deduce the theorem I mentioned. Okay, so I will not go further into that, but maybe I will just sketch you why the unimodularity is important to prove that this is a faithful normal trace. Okay, so because I think it's important. Okay, so this is the way you define your trace. Again, if you want more details, because I don't want to spend too much time on that, you can look at my notes and also in the paper of Aldous and Lyons I already mentioned, where this was first defined properly. Okay, so how do you, so faithful, so you should prove that faithful means that tau of t star, okay, so it will be non-negative, is 0. So, and is 0 if and only if t is 0. Okay, so how do you relate the unimodularity property to this property? So let's look at what is tau of t star. So this is the expectation under rho of the sum. If you look at t star, so my operator, so it's of the Dirac mass at O V of t t star. Sorry. T. Okay, I'll write it directly this way. It's an operator now. So Euclidean norm squared of this. So this is the expectation under rho of the sum over all V of the modulus of T, delta 0 T delta V squared. Okay. And call that I don't know, f of GO, okay, which is a non-negative number. Okay, so if tau of Toto star is T star, sorry, is 0, okay, if tau of Toto of T star is 0, then almost surely f of GO is 0. And then by the lemma, everything shows at the root, by the lemma, by the unimodularity lemma, which I called everything shows at the root, almost surely, for all V, f of G of V is 0, which means that it means that the Dirac mass, if you look at any vector, this is 0 for all pairs of elements. Okay, so T is 0. So you see how you prove that your operator is 0 by just using this the unimodularity. And for the trace, if you look at tau of T times S, so you use the same formula. So this will be the sum of Dirac mass at T, Dirac mass at V, S, Dirac mass at O. Okay, so this is the definition. Okay, so note that this is by Cauchy-Schwarz. This is a proper. It's convergent in absolute value. Okay, so and then I use unimodularity, which allows me to switch the definition, which allows me in this sum to switch the role of V and O. And so by unimodularity, you get the sum over all V of you switch S and V, and this is exactly tau of ST. Okay. And for the normality, it's just a monotone convergence theorem. Okay, so the fact that you have a nice trace on your fundamental algebra is really important. It is crucial that your measure is unimodular. Okay, I will stop here for this question of spectral of fundamental algebra, but we will see it appear again. Okay, so. Now, what we have seen is a continuity result for the a continuity result of the spectral measure for the weak topology. In fact, more is true, and this is what I'm going to explain, and it has very nice consequences. So let's call that convergence of atoms, or maybe I could write continuity of atoms of the spectral measure. Okay. Okay, there was nothing subtle in the previous continuity argument. Here, you will see there is a subtlety. I will state a theorem. Okay, let rho be a probability measure with a unimodular measure. Okay. Let Gn be a sequence of finite graphs. Let Gn be a sequence of finite graphs such that mu, such that Gn converge in the Benjamini-Schramm sense to rho, then the Kolmogorov-Smirnov distance between the empirical distribution, the spectral measure of Gn and mu rho, goes to 0. Okay, so the Kolmogorov-Smirnov distance is again we call as a Kolmogorov-Smirnov distance between two probability measures is a L infinity norm of the partition function. So this is a convergence. So the convergence in Kolmogorov-Smirnov sense is a convergence over all a bounded Lipschitz function. Okay, it's easy to see that this is also, you can also write it as a supremum over all the integral of f d mu minus f d mu, where f as a bounded variation norm distance of order 1. Okay, so if you don't know what is a total variation distance, bounded variation distance, this is a supremum over all T1 less than T2 less than Tn of the sum of f of Ti minus f of Ti minus 1. Maybe you put T0, which is minus infinity, and you put Tn, which is plus infinity, and you do this sum from 1 to n. No, maybe not for the... Okay, and you put absolute value here. Okay, so if f is as a derivative, this is simply the integral of the absolute value of the derivative, absolute value of the derivative. Okay, if f belongs to C1. Okay, maybe I think this definition is correct, but should have checked. Okay, so the Kolmogorov-Smirnov distance is it's a stronger distance than the it's stronger than the convergence for the over all bounded functions. In fact, there is a fact which a measure mu n converges to mu in Kolmogorov-Smirnov sense. This is equivalent to saying that mu n converges weakly to mu, okay, and that the atoms converge for all lambda in R, mu n of lambda converge to mu of lambda. Okay, so the convergence in Kolmogorov-Smirnov sense of measures is equivalent to the weak convergence. So it's stronger than weak convergence because this is clear from the definition. But it's what it adds with respect to the weak convergence, which is convergence of bounded continuous function, is a convergence of the atoms of the measure. Okay. So a corollary of this theorem is a very striking fact that if rho is sophic, so I recall you that sophic measure is a closure of all possible Benjamini-Schramm limits. Okay? If rho is sophic, then and lambda such that lambda is such that the spectral measure at rho as a spectral measure is positive, so there is an atom. If you have an atom of mu rho, then lambda is a totally real algebraic integer. Totally real algebraic integer. So let's call that this set A. Okay, so what is a totally real algebraic integer? It means that lambda is cancelled. P of lambda is 0 for some monic polynomial in Z of X with integer valued polynomial, and all Galois conjugates, meaning, so this is for algebraic part, and totally real. What does it mean? It means that all other roots of P are real. Okay, if all roots real value. Okay, so in fact, this is the same as saying that the set of totally real algebraic integer is the same as saying that lambda is an eigenvalue of a matrix, of a symmetric matrix with integer coefficients. Okay, this is equivalent to or lambda eigenvalue of a symmetric matrix. Symmetric matrix with integer coefficients. Okay, this is a set of totally real algebraic integer. Okay, so why is that? Because if my measure is Sophic, okay, then note that the atoms of mu of Gn, there must be, since Gn since mu of Gn, the atoms of mu of Gn are the eigenvalues of integer valued matrix. The atoms of mu Gn must be totally real algebraic integers. But since it converges in the Kolmogorov-Smirnov sense, the atoms, an atom of rho must be an atom of Gn, so it has to be a totally real algebraic integer. Okay, so that's a very nice fact. So maybe I should put some credit here. So this theorem, as it is written, is an extension of a paper by Albert, Tom, and Virag. Okay, so this is slightly more general than what I said, but in fact, the name to the technique of proof is an extension of what was known in algebraic topology as Luke approximation theorem, which I will give you the proof of that. Okay, so this is a very striking fact that when you have a Sophic, the atoms of a Sophic graph cannot be any integer. It cannot be any real number. It has to be totally real algebraic integer. Okay, and it's a conjecture to prove that for any unimodular graph, are the eigenvalues. So maybe I can write it. Conjecture for any rho unimodular. Mu rho lambda is 0 positive implies that lambda is an algebraic integer. Okay, this is also called. This is also open for groups. Okay, also open in the for groups. Okay, but if you have an element of the group algebra of a group, finitely generated group, that the atoms have to be located at algebraic integer. So I think it's called the algebraicity eigenvalue conjecture. Okay, and Tom has proved this conjecture, but this conjecture was true in the Sophic case. Okay, and that's what the way you prove that is by the proof. I will give you the proof of this conjecture in the Sophic case. Okay, so let's prove. So what is the key ingredient is the following lemma, which maybe we can credit to Wolfgang Luke. Okay, so you take lambda, a real number, You take theta and epsilon to be also positive numbers. Okay. Then there exists a continuous function, delta from 0, 1 to from r plus to 0, 1 with delta of 0, 0, such that if G has degrees bounded by delta, by theta, sorry, by theta, then mu of, so the empirical measure of the eigenvalues. Okay, so this is certainly less than mu G. So the function depends on lambda and theta. Okay, so it is not maybe I should write theta. Then for any epsilon, this will be more properly stated. So this is certainly less than the number of eigenvalues in the open interval lambda minus epsilon, lambda plus epsilon. Okay, but in fact, this is a part of the lemma. This is a part of the lemma. You can bound the number of eigenvalues in the interval lambda minus epsilon, lambda plus epsilon by the value of the atom at lambda plus delta of epsilon. It looks like a wrong statement. So in fact, this is true for any matrix whose operator norm is bounded by theta and integer values. Okay, so this okay, so also holds for A in Mn of Z with operator norm of A bounded by theta. Okay, it will be transparent from the proof. So this looks like a wrong lemma because it says that you can bound the number of eigenvalues in an interval, okay, around lambda, by the number of eigenvalues exactly equal to lambda up to a vanishing term. Okay, and this is uniform in the size of the graph. So it's uniform in M. So that's very striking. Okay, so I will prove the lemma, but first I will prove the theorem. Okay, so the theorem is where is it? Yes, here. But if you have a sequence of finite graphs which converge in the Benjamini-Schramm sense, then you have convergence in Kolmogorov-Smirnov sense. Okay, so proof of the theorem. Okay, so for we restrict to bounded degree graphs, to bounded degrees graphs. Okay, so I will restrict to the degree. I will assume that the degrees in Gn of A, in Gn are bounded by delta for all x and n. Okay, so I will. So the general case comes from a truncation argument, which I skip. You can find it in my notes. It's not interesting. Okay, so from the fact that I mentioned, it suffices to prove that the convergence of atoms. It suffices to prove, because we already know that mu of Gn, so it suffices to prove that mu of Gn of lambda converges to mu rho of lambda. Okay, because we already know this is what I just proved before, that mu of Gn converges weakly to mu rho. Okay, so we have to prove the convergence of atoms. I recall you the portmanteau theorem, the portmanteau lemma, or I don't know how is it called. So I think the name portmanteau was chosen by Feller or Billingsley, Feller, and so he credit portmanteau, who is supposed to be a French mathematician from Poitiers or Limoges, a small city in France, but there was never such man. So it's a kind of joke, the name of this lemma. So what is saying this portmanteau lemma is saying that if a sequence of measure converges weakly, this is equivalent to saying that for any open set, so it's equivalent to for any open set O open. So I always confuse, so I should better not. The limit of mu n of O is at least mu of O, and this is equivalent to for any closed set. The lim sup of mu n of f is bounded by mu of f. So C. Okay, so this is this portmanteau. So we already know the weak convergence. So we only have to prove that the limit of mu g n of lambda is, since we already know this one, we only have to prove that is at least mu rho of lambda. Okay. Okay, so but what to prove that? So it would be a consequence of the lemma of Luc. We know that the limit of mu of gn of lambda minus epsilon lambda plus epsilon by this is at least mu rho of lambda minus epsilon lambda plus epsilon, which is at least mu rho of lambda. Okay. Now we use the lemma, okay, but mu gn of lambda minus epsilon lambda plus epsilon, okay. This is so what is saying Luc lemma, but this is bounded by mu of g n of lambda plus delta of epsilon. Okay. Okay, so you have this bound, so you deduce in part. So therefore, the limit of mu gn of lambda is at least mu rho of lambda minus delta of epsilon. And this is true for any positive epsilon, and since delta continues and goes to 0, as epsilon goes to 0, you deduce the theorem. Okay, so let's prove the lemma. So now we prove the lemma. Let's look at it a second time. The lemma is here. We have to prove that if we have, if we fix a lambda and the graph with degree bounded by theta, we have to prove this inequality. Okay, that's the number of eigenvalues in the interval lambda minus epsilon, lambda plus epsilon, is bounded by the number of eigenvalues exactly lambda plus delta of epsilon. Okay, so that's what we want to prove. Maybe I can copy it. Okay. Okay, I will give you the proof for lambda equal to 0 because this is where it is simpler, but it extends to any real lambda. You can look in the notes. This is exactly the same proof, but so let's, for simplicity, assume that the spectra, the number of the size of the graph. Sorry, there is no n. Consider a graph with size n. Okay. Let's define the set, which is the interval lambda minus epsilon, lambda plus epsilon, without lambda. Okay, so sorry, our lambda is 0, so up in the general case, this is what you do. But okay, so you take this interval, so you have to prove that mu of I, mu g of I, is bounded by delta of epsilon. Okay, because you remove exactly this part, you subtract and you get. This is the question. You count that ni, which is n times mu g of I, be the number of eigenvalues. This is the number of eigenvalues in A. In I. So the number of eigenvalues of the adjacency matrix in A. Okay, so what is the crucial claim is that the product of all lambda I, if you look at the product of all lambda I, where lambda I is an eigenvalue which is different from 0, I claim that this is an integer, which is not 0. This is a crucial claim. Why is that? There are various ways to see that. One of them is saying that this product of lambda i's will be the derivative of the, if you take the derivative of the characteristic polynomial, if you look at the determinant of the characteristic polynomial, okay, so let's call that P of X. So P of 0 is a determinant, so it's a product of the eigenvalues. And the first non-zero derivative of P will be proportional to that guy. Okay, so it's easy. And of course, this polynomial is integer valued, so it's all its derivatives are integer valued. Okay, so that's one way to prove that. Okay, so the product of the non-zero eigenvalues, it's an integer, and it cannot be 0, so it's a non-zero integer. So in particular, the product of the lambda I non-zero, it's at least 1. Okay, because the integer set is fine, it's countable, so there is a gap between two successive. Okay, so it's at least 1. So this is the basis of this is the fundamental reason that the proof works. This is the quantitative repulsion of the eigenvalues. Okay, if an eigenvalue is not 0, it cannot be too close to 0 because of this constraint to be integer values. Okay, so now you write that this is bounded by the eigenvalues. They are bound, so you have n eigenvalues. So there are the eigenvalues which are among all the non-zero eigenvalues. There are the eigenvalues which are not in I, and in this case, they are at most theta, and the one which are in I, they are at most epsilon. Okay, because if so, I write that it's a product of the lambda I in I of the absolute value of I times the product of the lambda I not in I and different from 0 of lambda I. Okay, and those one, there is this number of such eigenvalues that they are bounded by theta, because my graph has bounded degree theta. So all eigenvalues are at most theta, and this one, since they are in I, their absolute value is at most epsilon. So you get that. Now you take the logarithm, and so this is even less than theta power n times epsilon power ni. Okay. And so I take logarithm, and I obtain that n log of theta plus ni, so which is n times nu of I of g log of epsilon is positive. So obtain that mu g of I is at most log of 1 over, that's a log of theta, log of theta divided by log of 1 over epsilon, which is my function delta of epsilon. Okay? So this is the proof. It's elementary, but it has a very striking consequence, and there is you can generalize relatively easily this argument to all lambda. Okay, now I would like to. So now you know everything I know essentially about the general theory of the relation between the Benjamini-Schramm convergence and spectrum, essentially. Now we will study the atoms and the existence of continuous parts in the spectral measures. Okay. I will start with some general facts on atoms. Okay, so let's call that atoms and eigenvectors. Okay, so let's, if you have the, so rho is my unimodular measure. Unimodular measure. Okay, so it's on my rotate graphs. So mu rho of lambda. So I recall you. So mu rho of lambda by definition. This is the expectation under rho of the spectral measure at the root of, you look at the mass of that. So if you remember, you can interpret an atom as being the projection of, maybe call it H lambda or E lambda. It's the orthogonal projection onto the vector space of eigenvectors. Okay, where E lambda is the set, is a vector space of lambda eigenvectors. Okay, so you can always interpret. So this is, you look at the orthogonal projection onto this vector space of eigenvectors, and the interpretation of the atom is an orthogonal projection of the root onto this vector space. Okay, so if you remember this, you can also, this is an element of your von Neumann algebra, so you can also write that as a trace of the orthogonal projection of this set. Okay, and this is called also this where tau and tau, this is associated von Neumann algebra. And this is a von Neumann dimension. So this is by definition, this is a von Neumann dimension of this vector space lambda. As a von dimension of a closed vector space is just the trace of the orthogonal projection to this space. Okay, and in another context, this is called the L2 Betti number. These elements are called in some context L2 Betti numbers. So I mentioned L2 Betti numbers because the original motivation of Luke was discovered this algebraicity of atoms. So original motivation of Luke was Wolfgang Luke's was, I don't know exactly why, because I'm not an algebraic topologist, but his motivation was to the study of the L2 Betti numbers. Okay, so why I'm saying that is this because you can always interpret. So the atom at zero are always related to eigenvectors. Okay, so in particular, if you have if psi is an eigenvector of so psi is in L2 V, so meaning that A psi is lambda psi, then since the spectral measure is a projection, it's at least, so it's a unit, let's assume that psi is L2 norm equal to 1, then the spectral measure at lambda is at least the orthogonal projection, the scalar product between psi and the Dirac mass squared. Okay. So this simple remark allows you to, because but we will deal when you deal with percolation graphs. So as soon as you have finite bending graphs, you will have atoms everywhere, and this is explained. Imagine that you have the root here. Here you have a finite bending graph. Let's call it T1, which has some okay, and here you have T2, which is, let's assume, for example, that T1 and T2 are isomorphic. Okay, so they are rooted. And here you have the rest of the graph. It can be anything. Let's say, for example, restrict to trees for simplicity. But if T1 and T2 are isomorphic, you can consider, so this is a root. Okay, you can consider a vector. Okay, if A of T psi, Ti psi is equal to lambda psi. Okay, so what I was saying, so if you have a vector of T1 and T2 are isomorphic. So if you have a vector, you put here psi over square root 2, and here you put minus psi over square root 2, and here you put the vector all 0 here. You will see that you have the eigenvector equation here, and since you have put psi and minus psi, you also solve the eigenvector equation here. So this vector will also be an eigenvalue. Okay, so when we look at, as soon as you have a kind of percolation graphs with many finite bending subgraphs, okay, so you will have atoms everywhere, even if your graph has an infinite connected component, you will have atoms everywhere, essentially at all possible eigenvalues of the finite bending subgraphs. Okay. So how bad is that? It's very bad because there is this theorem, which is by, it's a classical theorem by Bass, which has been refined recently by Justin Salez, which says that I recall you that A is a set of totally real algebraic integers, which we already saw, algebraic integers, which are the possible eigenvalues of integer valued symmetric matrices. So the statement of the theorem is that A is also the set of 3 eigenvalues. It's also the set of lambda, which belongs to the spectrum of some A, where A is an adjacency matrix of a tree, of a finite tree. T finite tree. So Richard Bass proves that for graphs, and Salez proved it, but it's even true if you restrict to trees. Okay, so a dramatic consequence is that, for example, if you take a corollary of this statement and the Luke approximation theorem, but if you take rho, which is, for example, a unimodular Galton-Watson tree with probability, with of degree probability pi. Okay, so I recall you that, let's say I will write, and the support of pi is included in contains, for example, 1 to the positive integers. then the support of the pure point part of the spectral measure is equal to all totally algebraic integers. So I will recall you what is the unimodular Galton-Watson tree. So you start with the root, and it has an offspring with probability with the number of offspring with low pi, and all the other one they have a number of offspring with low pi hat, which is a size bias of pi, where pi hat of k is k plus 1 times by k plus 1 divided by you normalize it so that it is a probability measure. Okay. So why is it so? Because if the support of pi is a positive integer, then the support of pi hat will be the all integers, okay, because there will be a mass at 0, because the pi hat of 0 is proportional to pi of 1, which has to be positive. So it means that your tree has finite pending trees, so that all finite pending trees, if you take any finite pending tree, it has positive probability. Okay, so and due to this this picture, you will have if you take any finite tree T, you will have this will occur with positive probability that the root as one of the subtree with 3, and one of the offspring of the rest, the remaining offspring of the root as one of its offspring with 3T2 with the same isomorphic tree. So due to this remark, you will deduce that the all possible totally real algebraic integer, which are eigenvalues of finite trees, could be an eigenvalue. And since we know that due to this Luke approximation theorem that possible atoms only are at a totally real algebraic integer, we deduce this equality. Okay, so the measure, the kind of probability measure that we are interested in when you speak about, think about random graphs, are very nasty and potentially have a lot of atoms. Okay. There have been some explicit computation of atoms. So there is some explicit, when restricted to trees, explicit computations on atoms. I would like to mention one theorem, which I will not prove because I want to focus on something else. But so it's a theorem which I proved with Lelange and Salez, which says the following: that you take rho, which is a unimodular Galton-Watson tree with probability distribution pi. Okay, you define phi to be the moment generating function of phi. So this is a sum of xk pi k. Okay, which is well defined on the interval 0, 1. And there is an explicit formula for the spectral measure for the atom at 0, which is quite complicated, but it's fully explicit, but it illustrates a phenomenon which I want to explain, where this function is a supremum of a function where f of x is a function which depends on the derivative of this generating function. So it's x bar. So x bar is, we define x bar to be a kind of conjugate of x defined by this formula. And it's phi 1 x bar plus phi of 1 minus x plus phi of 1 minus x bar minus 1. Okay, so you have an explicit formula which is complicated, but fully explicit for well, for the atoms at 0 of a unimodular Kelton-Watson tree. Okay, so I should it is not completely clear from this formula because, as you see, the formula is quite involved, but it gives some example. It gives some example such that mu rho of 0 is positive, but no finite pending subtrees. So where P0 is equal to P1, you can assume that, for example, the minimal degree is bounded by some number. So that you can find examples such that your graph has no finite pending subtrees. Okay, for example, it has even no vertex with let's say k minus 1 offspring, but nevertheless there is an atom at 0. Okay, so what I pictured here as being one possible source that the finite pending subtrees was one of the possible source of atoms. It's not the only one, and it's completely apparent even for 0. Okay, so because you remember this Lamplighter group where we have constructed transitive graphs such that the spectral measure was was only containing atoms, so it was pure point. But maybe we could hope that on trees the situation is nicer, but not so much. Okay, the situation is nicer. I will mention nevertheless a result of Sales, and I will conclude on atoms. There is nevertheless a general bound on atom, which is very nice. So which is due to Justin Sales. So you define I. You look at there is for trees, for general rooted unimodular trees, there is a general bound on the mass that the spectral measure can put at an atom in terms of the isoperimetry of constant of the tree and on the complexity of the algebraic complexity of the eigenvalue. So let me define that properly. So you define I of j to be for graph G to be its isoperimetric constant, which is you look at the infimum over all subsets of the graph, okay, which are of cardinal finite subset and non-trivial, okay. And you look at the one which has the smallest possible boundary. So delta of S is a set of vertices which are adjacent to S but not in S. Okay. So the theorem of Sales is that if TO is a unimodular random tree with low rho, okay, and almost surely the isoperimetry constant is bounded by some number I. Okay, I is deterministic. Then the spectral measure that you put at an atom is bounded by 1 over tau of lambda. I will define tau of lambda in 1 second. So this is the complexity of the eigenvalue, which I will define by okay, and there is another number. Okay, so we assume that almost surely the isoperimetry is bounded, and almost surely the degree of the root or any vertex, as we have seen, is bounded by delta. Okay. So you have a unimodular tree which is bounded, which has an isoperimetry, which satisfies an isoperimetry, and which has bounded degrees, and the mass of any atom is bounded by this formula. And what is tau of lambda? Tau of lambda is an infimum, is a minimum, it's an infimum over all trees, of all size of trees, such that lambda is an eigenvalue of the adjacency operator of this tree. Okay, T finite. Okay, so this is a minimal number of vertices. So this is the size of the minimal tree, which has as eigenvalue lambda. So he calls that the tree complexity. Okay, so a corollary of the result of Bass and Sales is that this tree complexity is finite for any totally real algebraic integer, and it says that the mass of an atom is bounded in terms of its tree complexity and the maximal degree and the isoperimetry. So consequently, to have an atom, this should be non-negative, positive, sorry. So if you call lambda p pure point of rho, which is the support of the pure point part of rho, this is contained in the set of lambda of totally real algebraic integer, such that tau of lambda is less than delta over I. Okay, so as soon as you have a tree with some isoperimetry, you can only have a finite number of atoms. Okay, so this is a very nice result, and okay, unfortunately I will not prove it, but because I have no time. But so this was to illustrate that on trees at least the situation is kind of under control, and we have a better understanding now on the possibilities of having atoms on trees, on unimodular trees. What I would like to do now is to move to the existence of absolutely continuous part in this spectral measure or continuous part. Okay, so I move away from atoms, and because we have seen this example of the Lamplighter graph group, which is a kind of general motivation of all this theory, is to try to we know that there are transitive graphs with pure point spectrum, but we would like to understand, can we find some geometric criteria which implies existence of continuous parts? Okay, so this question goes under the name of quantum percolation. So as its name suggests, it was introduced by physicists. Okay, so after the work of Anderson, the classical one, I think in '56, and the work, I think the term quantum percolation comes from Dejean, Lafont, and Millau in paper in 58, so it's a long time ago. Okay, so because in physics, in statistical physics, you are interested in Hamiltonian and the way which is you are interested in an operator which is Hamiltonian, and the eigenvalues. If you want to understand the behavior of a particle, which is submitted to this Hamiltonian, you will have to understand the eigenvector decomposition, in particular, whether or not you have pure point spectrum or some absolutely continuous spectrum or some continuous spectrum. Okay, so, and in Anderson motivation, he was mentioning, I think, problem of conductances in lattices with impurities, and it became a problem of the fact that the existence of a pure point spectrum or versus existence of a continuous spectrum could be translated into the fact that the media was an isolant or had some nice conducting properties. Okay, I'm not a physicist, so I should not say more about that. This is still a very active topic, and there are maybe the most important problems of mathematical physics can be one of the most important problems in mathematical physics can be translated into problem of quantum percolation or related notions. Okay, so first, what is classical percolation? So in our framework, so we take rho which is a law of GO, okay, which is, let's say, unimodular. Random, okay, so we have a unimodular random routed graph. Okay, so what is classical percolation, which I will call, let's say, CP? It means that you will have percolation if the probability that the graph, the number of vertices is infinite, is positive. Okay, so you will have percolation is simply the classical percolation is simply the problem that connected component, if you have a graph, that the connected component of the root is infinite with positive probability. Okay. So this is the classical percolation problem. So you can think of rho as being, for example, the law of you take the percolation on ZD with some parameter P, and you look at U of G. So you can you look at the connected component of the root of the origin, and you root it at the origin. Okay, so you can think of that. So you make the infinite grid on D dimension. You keep each edge with probability P, and you look at the connected component of the root of the origin. Okay, and this defines a unimodular random rooted graph. And so the percolation question is whether or not, so here it will be depending on the value of P, whether or not with positive probabilities there exists, sorry, I put 0, but I should put infinite, whether or not with positive probability, the connected component of the root is infinite. Okay, so I've rewritten this question in terms of our framework of unimodular rooted graph. Okay, so what we call the AQP, the average quantum percolation. So the word it's not very average quantum percolation. What does it mean? What is the definition? We say that there is quantum percolation on average is if mu rho, which is the average under the measure rho of the spectral measure at the root, okay, as a non-trivial continuous part. Okay, so I recall you that if you have any measure mu on R, you can decompose it as a pure point part plus a continuous part, which you can further decompose it as a pure point part plus a singular continuous part plus an absolutely continuous part, where the absolutely continuous part is a part of the measure which has a density with respect to the Lebesgue measure. So it's a Radon-Nikodym derivative of the measure with respect to the Lebesgue measure. Okay, so you will say that you will have average quantum percolation if the expected spectral measure at the root has a non-trivial continuous or absolutely continuous part. Okay, and the quantum percolation per itself in our framework, we can define it as the fact that with positive probability, the spectral measure at the root, let's say the continuous part, is non-trivial, so as a positive mass. Okay, so in words, I say you will have quantum percolation is with positive probability, the spectral measure at the root as a non-trivial continuous part. Okay, so I have three notions: classical percolation on connected components, average quantum percolation on the spectral measure, and quantum percolation on the spectral measure at vectors. Okay, it is quite clear that quantum percolation is a refinement of average quantum percolation, which implies classical percolation. So what is that? This is why it's Fubini. Okay, because Fubini's theorem will tell you that if you have a continuous part which is non-trivial of the random measure, so this is a random measure. When you take the expectation, it will again be a continuous. Okay. This is Fubini's theorem, and this part is just a remark that if G is finite, So to check this part, it's just the remark that if V of G is finite, then mu of U of G, okay, which we call the rho, mu rho, is pure point, it's purely atomic. So almost surely. So then mu rho will be purely atomic, and when you take the so mu of G, the spectral measure at G is purely atomic. And when you take the expectation, when you take a sum of a countable sum of purely atomic measure, if the sum is countable, you will still be purely atomic. Okay, so since there is only a countable number of finite graphs up to equivalence classes, there is a countable number of unlabeled rooted graphs. You will deduce that if you are if there is no classical percolation, the average the spectral measure has to be pure point. Okay, so you get this sequence of implication. Now I will try to what time is it? Oh, okay. I was very slow. Okay. I have 5 minutes. Okay, maybe I will try to tell you quickly the results we know, and some of the results we know, and I will prove some of them next time. Okay. So what? So let's call that some results. Some positive results. So I will give you first a theorem on percolation on ZD. Okay, so I will recall you, if you look at percolation on ZD with parameter P, there exists a parameter PC, which depends on D, okay, which is positive and away from bounded away from 1, such that if P less than PC, almost surely you have no infinite connected components. And if P is larger than PC, almost surely there exists a unique infinite connected component. Okay, so this is the most basic theorem on fundamental theorem of classical percolation. So we have proved with Arnapsen and Balin-Virag the following result, which only works unfortunately in dimension 2, as you will see in the proof, but we will see next time. But how does it say? That if, so you restrict to if P is less than PC, then mu rho is purely atomic. So this is trivial, purely atomic. From what I said, so the theorem is that if P is larger than PC, so then mu rho is as a non-trivial continuous part. Okay, so in fact, for t equal to 2, we know a result which is we know exactly what happened at p equal to pc, so you can write that. Okay, so this theorem solves the questions of average quantum percolation in dimension 2. And it says that the percolation, the threshold from average quantum percolation coincides with the threshold of quantum percolation, or for classical percolation. Okay, so now I don't have even time to quote the next result. So, so I should say that this is only result. So the case D larger than 3 is completely open. Okay, and maybe I can also say that for existence of an absolutely continuous part, this is also open. Okay, because our theorem will only prove the existence of a continuous part, not an absolutely continuous part. So it does not discard the possibility of having a singular continuous part only for P larger than PC. Okay, so next time we'll see a proof of this theorem and of another one, which I will state next time. And then we will move to finite graphs and the edge of the spectrum for the rest of the course. Okay, so thank you. If you have questions, that's a good time.